Hi, everybody, and welcome to the January 2022 CBEC joint meeting with CSI. We have our speakers and our sponsors all lined up, so I'm going to go through a little bit of an introduction and then hand it off to Matt from CSI. As I'm sure most of you know, CBEC is a nonprofit dedicated to promoting the pursuit of excellence in building design, construction, and other technical aspects. So we're here to just kind of share information as much as we can. We do that with the help of our board members. Many hands make light work of getting events like this together, and maybe even a symposium in 2023. Our next meeting is our February meeting. We've got Rocco Romero from WJE, who is presenting on aluminum window sill anchorage and supplemental waterproof flashing design practices, which should be really interesting. We had an aluminum window sill guy sponsor a meeting a year ago. Other events in the area, CSI Puget Sound's next meeting is looking at interiors, a virtual tour of Coriander Designs on February 12th. And then I will hand it over to Brett Check from AZEC to give us his quick pitch, and then we'll jump over to Matt Gregory from CSI.
Hey, good afternoon or good evening, everybody. Let me just pull this up real quick. All right, does that look okay?
Perfect.
Perfect. I just got a couple of minutes with you guys. I wanted to introduce myself. My name is Brent Check. I'm the Market Development Manager here in Washington. I specifically handle our trim and siding division. If you're familiar with AZEC, we also have a decking and an outdoor living division. But for today, we're going to focus a little bit on the siding and trim portion of it. Kind of diving into it, if you're not familiar with AZEC, generally between our decking and our siding, we use a combination of polymer products as well as composite. On the exterior side, basically anything that goes vertical, it's going to be 100% polymer. So what does that mean in comparison to alternative trim substrates, whether it be wood, fiber cement, paneling, manufactured, EPAs or different things, a couple different things. So AZEC PVC trims and sidings are 100% resistant to moisture. They'll never absorb moisture in any sort of capacity. They're resistant to mold, and because of that, their weather's better, especially here in the Pacific Northwest. Any sort of water getting to wood trim, fiber cement, trim, other materials, it wants to wear it down a lot sooner than our product will. High workability with our products. You're going to be using the exact same tools, exact same fasteners you would be using, and we'll touch a little bit on that here in a couple of minutes, but it's very easy to use, very easy to cut, very easy to miter, very easy to design in specific applications. Fewer installation restrictions, meaning that we can be installed on ground level, we can have grade contact, we can go straight to masonry. We have basically no restrictions like other manufacturers do. And we have efficient fastening, where on certain manufacturers' products, whether it be wood or fiber cement or others, you can split the products. We want you to fasten as close to the edge as possible. You're never going to split our products, never going to be an issue with regards to that. One of our main pushes right now is going to be our AZEC Paint Pro technology. If you're not familiar, if you've used James Hardie before, they're having incredible difficulties, like a lot of other manufacturers, providing materials on both the commercial and multifamily and residential perspectives. Our Paint Pro technology is nominal trim that is specifically designed to take paint, no primer, no sanding, and it's got incredibly higher, superior paint adhesion and low maintenance. So if you put it up on the wall, as it lasts, all you got to do to clean it is take a brush and some water to it. Like I said, benefits: it's impervious to moisture, paint adheres well. A big thing of why I left this slide in here is it's got a Class A flame spread rating, which is a big point that people ask. So it's easy to get specced on multiple projects. And of course, you use mechanical fasteners like you would use with other materials. So when you're using PVC trims, this top left corner, you're going to get quality. It's going to reduce waste. Every single one of our products comes out perfect, ready to go. We're not going to rot, splinter, or split, delaminate, warp, or swell from moisture, because like I said, we're impervious to moisture, impervious to mold. Like I said, we're suitable for ground and masonry contact. No need for ugly clearances. No special tools required. Whatever tools you have in your garage or in your truck, that's what we're using. You don't have to use a respirator or special ventilation, and no harmful dust. Cut ends do not require paint for protection. So if you're cutting ends, you don't have to prime them. We're already primed. And again, our products are 100% recyclable that we'll get into real quick. this is just a quick thing. It's a test over 24 months with each section on the far left, a control, and then what it looked like 24 inches or 24 months down the road. Basically goes to show that the AZEK pieces on the left here, they're not going to weather in comparison to wood, which is very popular up here, depending on what you're doing. This could even be the case if we held fiber cement up here, which is very popular on exteriors. Another thing to match is we do have shingle panels. You'll see this top, well, I guess it'll be, we have the most popular one in this area is going to be 7-inch reveal, 100% polymer. They've got varied keyways. They're about half the weight of fiber cement shingles, which are very popular up here. But it's been a great product for us, a great push. One of those projects, we just finished this project here a couple of weeks ago, or a couple of months ago, rather. It's up on Whidbey Island. Like I said, we do a lot of different projects, whether it be custom homes, it can be commercial buildings, it can be multifamily, it can be really anything that you can use our products. This particular house, every single piece on this outside, except for the soffit, is AZEK. It's AZEK trim, it's AZEK shingle, and it came out looking really well. Depending on what your scope is these days, board and batten has become very popular. So we do have sheets up here, 4x8s. We can get bigger. We also have batten strips. We're finding that the design for especially residential homes this year or recently is lots of different types. You got a shingle up here, you got a panel up here, you got lap siding down here. So board and batten's been very popular for us. And another really popular thing for us has been high performance cladding systems. These pieces and these projects that you see here are ones that are around here. It's literally just using our decking as cladding. You're taking our PVC decking and putting it up on the wall on some furred strips using our Cortex fastening system. Incredibly easy to use. So, and then last but not least here is our AZEK full cycle rip program. I get a lot of pushback sometimes. People go, hey, we got to follow certain green restrictions, certain lead restrictions. Well, we have committed, we're a publicly traded company. We own our own recycling plants. If you have a project that uses PVC or AZEK trim, we'll send these bins out there. We'll take any plastic back, recycle 100% of it back into boards. So you're contributing not only to long-term, there's no more deforestation, or we're reducing greenhouse gases by coming back and doing redos. If you're recycling your PVC projects, you're not going to have any issues. And like I said, you're one of the greener products out there. We have a full line of products. I didn't have a slide big enough for it. We've got windowsills, we've got crown moldings, we've got brick moldings, I've got beadboard, I've got shiplap, I've got quick corner. So we've got a whole bunch of different things that if you have any interest, that you can reach out to me. I'm happy to get you specific information on samples and or literature. And like I said, we are a decking company as well, TimberTech AZEK. This just kind of shows, I mean, that's probably what we're most known for in the Pacific Northwest is our decking. Lots of different information on there. If you have any questions, let me know. And again, interest of time. If you have any questions, here's my name, here's my personal phone, here's my email address. I'm local out of the Kirkland area. I cover the entire state of Washington. If you have a project you want me to come take a look at, if you have a job you want me to come sit down in your meetings, I also offer Aia presentations if we want to set something up further down the line. Please don't hesitate to reach out. I'd be happy to help spec some of our products. So I think that's my time, but I really want to appreciate you guys having me here today. Like I said, any questions, please don't hesitate to ask or reach out.
Great. Well, thanks so much, Brett. Matt, do you want to jump in? I don't know if you have any slides to share. Or if you want to, Matt, you are muted, or if you want to introduce Beth.
Oops, can you hear me now?
Yep.
All right, I'm on my phone. I apologize for being on my phone. For some reason, my laptop's not allowing me to speak or show video. But I do want to give you guys all a welcome from the Puget Sound chapter of CSI. And we are have a long history in the Puget Sound area and share part of the Puget Sound with the Mount Rainier chapter. Beth has been our go-to person to set up this meeting, but she's also our chapter sponsor, and I want to give her an opportunity to speak about her firm. Beth, are you ready to do that?
Yes. So my name's Beth Stroshane. I own Applied Building Information, which is a local specification firm, and we recently updated our website that so now it looks as cool as we are. We've got 8-person staff and help manufacturers write product specifications, help large institutional clients write master specifications and help design professionals write individual project specifications. So if any of that sounds like what is on your to-do list for this year and you want some support with that, let us know. And thank you for joining us for a CSI CBEC presentation where we're going to learn about, the Pacific Northwest two favorite things, wood and glass. So thanks for joining us tonight. And everybody knows that's what we're all trying to figure out how to do. And since it rains here, trying to get our wood and glass installed in the rain so that it still looks as cute as it did when it came on the truck is part of what I would love to learn today from Janelle. And Richard is the guy that, designed the glass floor in the Space Needle, if you didn't know that. So there's lots of excellent information available from our two speakers, and they're both like wonderful people that I've known for a very long time. And so ask them questions, be interactive. They're both excellent people and you'll leave with great resources to use in the future. So thank you all for joining us, and we'll see what exciting things happen from my favorite wood person and the guy who designed the glass floor in the Space Needle. If you haven't seen it, you should go see it someday. Okay, now I'm going to hand it off to Janelle, who I think is our first speaker. Or are we supposed to introduce Janelle?
Yeah, if you would like to introduce Janelle, that'd be great.
My introduction of Janelle is that Janelle was an envelope consultant who studied failures before she learned about wood. So she is a brilliant speaker for this. She's now out of Portland. We went to college together a very long time ago. And now she is the person that we all get to call about tall wood structures, or just how to make wood not rot, or all kinds of other good stuff. So I'm going to turn it over to Janelle to probably tell you all about her more recent, wonderful things, as opposed to, the long time ago wonderful things that I know.
Right, Janelle, take it away.
Thank you, Beth. Thanks for having me here today. Again, my name is Janelle Leafblad. I'm the regional director for WoodWorks. Let's see. Can you see my slides yet? Probably not.
I think I see topic: priming mass timber projects for success.
All right, great.
Yeah, that's still my slide though.
Okay.
Oh.
There's Janelle's
There's
slide.
my slide.
I'm helping.
Right.
No, I'm not
Great.
helping at all. Carry on.
Okay. So if you haven't heard of WoodWorks before, we are a nonprofit. We're set up by the timber industry at large to be a one-stop shop for technical questions. Like Beth mentioned, my background is in forensic engineering, structural engineering. I have a master's degree in wood science. I love to talk about wood 24/7. So don't hesitate to give me a call. I'm your free wood consultant. You can think of me that way. And we're here to help. And so Beth and I chatted about the program tonight. And this is a brand new presentation that we put together recently. So I'm going to try it out on you guys. Thank you. All about the key early decisions for really making mass timber a successful project. And we've certainly had a lot of those here in the Pacific Northwest. Kind of the whole impetus across the country started here. So we're certainly seeing a lot of good things. This is an AIA accredited talk, which means that it has a course description and learning objectives. And I'm happy to give you AIA credit. If you want to drop either Beth or Nathan a note and let them know that you'd like a certificate from tonight, I'm certainly happy to provide an hour's worth of credit.
Yeah, we should have a list of all people who should have put their AAA numbers in when registering.
Perfect. We will get that reported for you.
Yep, great. And I forgot to mention, if you guys during the presentation want to use the Q&A at the bottom of the screen to ask questions, we can bring those up to the panelists as we go. So thanks.
Yeah, certainly. Bring up questions as you think of them. So when we talk about building a building with mass timber, I think this is no shock to anybody. I think any consultant on any project of any type is always going to tell you the earlier you can bring me on, the better this project will be, right? So this presentation is really geared around those early decisions. And my colleague and I tried to make a little decision tree map of what's the single most important early design decision on a mass timber project. But it ended up looking like this spaghetti splatter of decisions, because they all interact with each other. So, is it the construction type? Is it fire? Is it acoustics? Is it MEP? Is it building envelope design? How are we going to connect things? How are we going to penetrate things? There's a lot of decisions, and they all set each other up for success or failure. So, let's just dive into it, thinking about how they all are interconnected and they all need to be weighed. Like I said, I think we're all going to place an emphasis on the word early. And with mass timber, we're making these huge design decisions early in the design process, sometimes a lot earlier than we're used to making decisions, because they're going to start cutting your timber specifically for that job. There's no going back once they start doing that. So when and how we need to involve a contractor or a developer or a fabricator or mechanical engineer, we have certain assumptions that the way that we've been doing things is the way that works for all projects, and it may not work necessarily so great for your mass timber project. So with mass timber, we're trying not to rely on default assumptions, and we need to be willing to make early decisions in a different way than we typically do, because that's going to allow for greater efficiency, allow for greater integration, especially with 3D building models, and more coordination with a contractor and a fabricator, and ultimately leads to better project success down the line. Again, here's this emphasis on the word early and how it relates to this efficient master project. And what we're really trying to do here is be efficient and optimized for a mass timber design. I sat in a meeting earlier this week and talked about how like efficiency in choosing a commodity project or commodity product is different than when you're working with mass timber, which is not a commodity project. It's actually more efficient. You'll get a more cost-effective project if you actually pick your manufacturer early. And I know on public projects, you can't always do that. But when you're efficient with your product, then you can realize cost efficiencies, you can realize material use efficiencies, construction speed, and minimize those RFIs. So the key takeaway here is just to commit to a mass timber design from the start. And I know that not every project can do that. So I'm going to propose that we sort of take a look at our spaghetti map of design decisions, and I will suggest to you one potential design route that I personally really like, which is starting with the building size, because that informs, together with the occupancy, it informs our construction type and grid. The construction type and grid really inform our fire resistance ratings, and the grid and the fire resistance ratings really inform what the timber member sizes are going to end up being and our MEP layout. But that's not all we're going to think about. We're going to talk about acoustics. We're going to talk about fire resistance as when it comes to connections and penetrations. And then we'll also talk about MEP layout. And there's certainly a whole lot of other things to talk about. This is actually a 2-hour presentation that I've made into one for you. So any structural engineers in the room will notice that I'm going to leave out lateral system design. That's an area we're not going to talk about tonight, but I'm happy to talk about. As Beth mentioned, my background is in building envelope design. So it's something that is incredibly important to me personally, and it's incredibly important to these mass timber projects' success. But I wouldn't say that we often put it at one of these key early decisions. And I would like to see a reversal of that. In building envelopes with mass timber systems, we're seeing definite benefits in prefabricated facade panels, whether that's wood or non-wood. We're seeing benefits in energy efficiency, and I put on the slide here, CLT is helping us with our R value. It doesn't get us all the way for sure, but it does help with our R value instead of hurt it. And then we have the opportunity, unlike in light frame construction, where we're stuffing our stud cavities with insulation. In mass timber design, we're looking at continuous insulation, and we're keeping those control layers installed on the outside of wall panels. So we have the ability to do those perfect walls and roofs that we talk about a lot, but don't often get a chance to do as building envelope engineers. So there's a good thing here. On the other hand, we want to be very careful to consider that moisture management during construction is definitely on a risk spectrum. And what we're used to doing in light frame construction, maybe even what we've come to be used to doing in the Pacific Northwest, does not translate necessarily when it comes to mass timber. Yes, your panels can get wet, and that's okay, but they take a long time to dry out. So being aware of that, aware of how to protect your materials, and not just your mass timber, but your steel connections, things like that. Protecting your materials is really important. And then getting the owner ready to accept what happens with natural materials, like splitting and checking, and being aware of what those mean when it's a problem, when it's not a problem, and how long it'll take the building to come into equilibrium. So I can talk about building envelopes all day long, but I am certainly going to pass that buck when it comes to others in this industry, and particularly in the mass timber industry, that have been doing this for a while. And I'll give you some resources at the end in particular to point to. So that was a lot of background to say, let's push the start button and find out how do we actually dive into the building code and really understand all of this. So remember that I said I really like to start with the type of construction. I feel like that choice alone leads you down so many paths that you don't get to take back later on. And so to me, it's a key early decision. So we turn to Chapter 6 in the International Building Code, and we basically have 8 options for construction type. This pullout here is not direct from the code, it's a compilation table, and it's showing basically what's in the 2021 IBC, but it's also showing what's been in the 2015 and 2018 Washington State Building Code since 2019. So with the new types of mass timber construction in the breakout categories of type 4. But you can also use mass timber in type 3 and type 5 construction really easily as well. So don't feel like just because you're going to do a mass timber project, and maybe it's your first one, that you're boxed into a corner in terms of type 4 construction. There's a lot of different nuances to where that's going to go. And for low to mid-rise mass timber buildings, there can be lots of multiple options for construction type. There's pros and cons of each. Don't just assume that one type is always best. And you can always call me to like spitball around this. I'm happy to talk about it. And then looking at those 8 options for construction types, you're going to see highlighted right here in yellow. Then there's corresponding fire resistance ratings. So basically you're going to run the gamut of 0-hour ratings all the way to 3-hour ratings for type 4A, and then type 4 HT is kind of in the middle somewhere. No prescriptive fire resistance ratings, but meeting minimum sizes. So again, construction type really drives what the required fire resistance ratings are. And then knowing what those fire resistance ratings are is going to start to inform the most efficient mass timber elements that we're using. And we'll talk more about that specifically. But if I had to like wrap up what this whole presentation is in just these 5-minute discussion points, it would be starting with those 3 key decisions. Start with your construction type, that informs your fire resistance rating. And then your fire resistance rating is going to start to inform the size of your panels and the size of your beams and columns. So we'll get into some more specifics. Let's talk about code. That's everyone's favorite, right? Let's talk about code. So mass timber products are defined in Chapter 2 of the IBC, as well as in Chapter 23, the wood chapter. They're defining the products in the building code that can be used in these construction types that allow combustible materials or heavy timber, where the definitions in Chapter 6 really come into play. So just a brief highlight, yes, you can use mass timber in types 1 and 2 construction as well, types 1B and types 2A and B. You're basically limited there in terms of using them in the roof. So types 3 construction, types 4, and types 5, those are the systems where you can use the entire building structure as mass timber if you want to. I'm not saying that you have to. I fully support hybrid structures. Go for that. Use material where it makes sense. But if you wanted to do 100% mass timber structure, you could do it in those categories, types 3, types 4, and types 5. In addition to that, I've alluded to this, that there are these new options for tall mass timber construction in the 2021 IBC and earlier in the Washington State Code. You can see here in the graphic showing 18 stories for type 4A, 12 stories for type 4B, and 9 stories for 4C. Of course, there are further limitations on occupancy types. So those story limitations are around, you'll see it here on the graphic, office, assembly, residential, mercantile is a little lower. And certainly I have whole presentations that go into just this thing. But it's a pretty exciting development, and I just want to pull out one thing that I get asked a surprising amount is, are we limited to 18 stories? And the answer is no. You've got 270 feet in this type 4A category. Maximize it. It doesn't have to be 18 stories. It could be 18 stories of mass timber on top of concrete podium provisions in 510.2. You're not limited to that. The other thing that's really changed in the code is around concealed spaces. That's been one of the historic limiting factors, one of the downsides of type 4 HT construction, that, you know, if you wanted to have a drop ceiling, that was not going to be allowed. Up until the 2018 IBC and the previous versions, type 4 HT construction was called out as without concealed spaces. So when we got that into our head as designers, I think people tend to pull away from type 4 construction in general. But with the recent code updates in the 2021 IBC, there are provisions for concealed spaces now. There's basically 3 options for doing that. The first option we're seeing here is just extend the sprinkler coverage within that concealed space, which incidentally is the default in NFPA 13 provisions anyway. We just get around it so often in construction, we forget that it's actually the default. The second option is to fill that concealed space with non-combustible insulation. And then the third option is basically not to have a combustible surface within the concealed space. So to cover up all of the mass timber with a layer of 5/8 inch type X gypsum wallboard. So those are basically the 3 ways to achieve concealed spaces, not only in type 4A, B, and C, the new type 4 provisions, but also in type 4 HT projects. We have a whole white paper just on this if you want to know more about concealed spaces. So let's get into fire design. You know, I think that this is a question that comes up a lot with people who are unfamiliar with how timber works. I've been in the timber industry a long time now. I did, even in college, I was working at a lab, doing some of these tests. We have tested wood in fire situations for a very long time. And so what you think you know about how wood burns in light frame is really different for mass timber. It burns really slowly and predictably. We'll look at how to calculate that in just a minute. But let's again step first into the code. And so we have these options, these new options in type 4. We still have options in type 3 and type 5, as well as those roof options in type 1B and 2A and B. And again, there's that gamut of running anywhere from 0-hour protection all the way up to 3 hours of protection. So how do we achieve that 0 to 3 hours of protection? So the type 4 HT is the only one that has minimum sizes, and it does not have a fire resistance rating. The two are not actually equivalent, but they are allowed in the code. Other than type 4 HT, when you're looking at those other construction types, then you need a demonstrated fire resistance. So the way you demonstrate fire resistance is through calculations or testing. There's actually 6 different ways that we can show a fire resistance rating per the code. I think we're super used to showing tested assemblies, and that's our usual go-to. But with wood, the calculation approach is also a valid way to do it. And it's certainly something our structural engineers are getting more involved in, because that's in the NDS chapter 16. So you follow that code path, starting with the IDC chapter 22, that points you to the NDS chapter 16, that's the fire chapter in the National Design Specification. Or you can do tests in accordance with ASTM E119. So notice that that doesn't say a UL test, it says ASTM E119. There's lots of laboratories that can do that. And so in the wood industry, that's really common that a lot of different laboratories will do that. So to that end, there's that code path again for the code path for a calculated approach. But I wanted to point out that tested assemblies are also really common, and that they've been done a lot by industry and manufacturers. And WoodWorks, we collect all of the ones that we know about, and we put it out there for you in one spot that you can find these tested assemblies. So we've consolidated that, and you can ask questions like, you know, I need a mass timber floor panel that needs to have a 1-hour fire rating. What are my options for that? How thick does it need to be? What do I need to apply to the top layers, and etc. So I think there's over 50 mass timber tested assemblies, fire tested assemblies in this document. So it's a really good resource. I can give you a link to that. It's right on our website.
Now,
So
Beth was asking about using spray applied fire resistant materials in lieu of like the 5/8 or in these assemblies.
Yeah, I think that that is certainly a growing interest. I will say that the code equivalence for that is it's really difficult to meet. And I find that a lot of manufacturers go part of the way to showing equivalence, and very few of them go all of the way. So I think it's hard to take to jurisdictions full proof that it meets code equivalence of a fire retardant treated material.
So it's not the same as a thermal barrier over insulation on the interior. It's different than that.
Correct. Yeah.
Okay.
Usually they're talking about equivalence to FRT, fire retardant treated. The code prescriptive language alternate to that is talking about what equates to gypsum board protection, passive protection.
Okay.
Okay, So we also have a really great white paper on the fire resistance rating design of mass timber. Again, that's available for free download at our website. All right, so we've made it here. I feel like I'm quickly running out of time and lots to talk about. We've made it to the structural grid. So since we've talked about construction types and now we've talked about fire resistance ratings, the next thing in my particular flow chart we're going to look at is the structural grid. And, you know, what are the dimensions between columns? What are the dimensions between beams? Is it a girder system? Is it a girder plus purlin? As we look into this more, we'll start to see how do we lay out these relative to each other. Are they stacked on top of each other like this image is showing? Or is everything flush top to the underside of the mass timber floor panel? When it comes to grids, when you're laying out a structural grid and the resulting spans of the elements, both the beam as well as the panel, I think one thing that we want to consider is repetition. One thing I talk about a lot with designers is manufacturers' capabilities. Like I said, mass timber is not a commodity. All the North American manufacturers need to meet the APA PRG 320. So you spec writers, that's an important line item to make sure when you're writing in your spec. The APA PRG 320 is an incredibly important document, it has different years. The latest one is the 2018. But that's a manufacturing standard, but it doesn't limit manufacturers to, say, a consistent panel in terms of not everybody's making the same width, not everybody's making the same length. Every manufacturer is a little bit different. And so, you know, when we talk about manufacturers' capabilities and what panel sizes they're producing, and it's not just the length is important, but also the panel widths. And that informs our grid layout. Like, is it on an increment that's efficient for the manufacturer to produce both length and width? They're going to produce a whole size panel. And if your project needs to cut that panel, you've bought the whole panel and you're paying for that cut. So that's why efficiency is so incredibly important in terms of your grid. You know, with steel, it doesn't matter as much because we're trying to bury, when we're doing steel design, we're trying to bury steel columns in the walls. We're thinking that we're already going to have drop ceilings. We don't often see steel beams, but with mass timber, you're going to see all of that. You're not going to be hiding them necessarily in the walls. You're not going to often have drop ceilings. People like to see it, so it's not always going to be concealed. We often see the beams. So having a repetitive column and grid spacing, the beams, the girders, all of that's going to look cleaner, in addition to the cost efficiencies that you realize. So if you can really dial in that grid layout from an efficiency perspective, that's going to help on the cost perspective too. So here's a different project which has a grid that's all over the place. These grids on 24 feet, 26 feet, 40 feet, 14 feet. We're really varying this. I would say this is what we commonly see for a structural steel building. It's basically taking the architectural floor plans and then forcing a steel grid on top to fit the columns within the walls, right? That's usually the way we do it in structural steel design. But with mass timber, we're really just wanting to optimize it and design it as mass timber from the start, and then can we adjust that column grid to be more efficient with mass timber? I feel like it's really important for a first-time developer client, take them out to see one of these buildings, see the space, because sometimes when we're talking about like 20 by 20 or 20 by 30 grids, developers get nervous around what is that going to be like for my space when I'm used to these bigger spans that I've gotten from steel and concrete. But I will say, having this uniform, clean grid is just, it's going to look better, it's going to feel better, and the space is not going to look too small. I guarantee you'll feel that way the first time you're in one of these. So
Hey,
let's do,
Janelle, we've got a question that is, what are the typical manufacturing sizes? I mean, is there 5s and 4s and 6s, or 4.5 and 3/4?
It's so crazy. So the smallest width is 4 feet. The widest width is 12 feet. So it's kind of like there's a few manufacturers making this 4-foot panel, and there's a bunch of manufacturers making anywhere from an 8 to 12-foot panel in a whole lot of increments in between there. Okay. And then the length varies even more because that's your press length. So it varies anywhere from, I used to say 23 feet, but I think they have a longer press now. I will say that it averages 40 feet, but then we see 52 feet, and we've seen as long as 60 feet. So there are a couple of mass timber structural engineering firms that they do this in-house now. They have their own calculators. Fastenep has one on their website that you can play around with that's really kind of fun. And they sort of focus on this sizing of efficient spans, because it's not just about those panel lengths. Those panel lengths are actually, going to dictate to you how often you have those girders or purlins spaced, and they're also going to dictate to you like how deep they become, right? How deep your beams become. So I'll just give you an example here. This is a project where it's maybe a 5B construction or a 3B construction. So that means that it has a 0 fire resistance rating. That's really nice. We can go to if we can go to the thinnest panel possible, that's probably going to be efficient from a cost perspective. We know that for sure. So if we're going to look at a 3-ply CLT panel, if anybody's interested in this, we can obviously discuss this on a project by project basis, but we also have an Ask an Expert article on our website that discusses this. Generally speaking, a 3-ply panel for floors is efficient in the span range of 10 to 11 feet, maybe up to 12 feet, but generally we're looking at 10 feet is a very efficient span for a 3-ply panel. That sounds really small, right? But I've seen these amazing projects where you've actually got these timber bents of, 40 feet in one direction, 30 feet in one direction, and then they're spaced every 10 feet to maximize to that thin panel. So knowing that, if we're going to use that thin panel, we want to lay out our grid in some type of increment of that 10. So maybe we have a 20 by 20 grid. That's what this project that's shown on the screen is. This is Albina Yard in Portland. It's a 20 by 20 grid and 1 intermediate purlin in every bay. Another example, maybe we do a 30 by 30 grid as we're seeing on this project. This is Plat 15 in Denver, Colorado. This is 2 intermediate purlins per bay. Again, we're laying out our columns. Our columns don't necessarily have to be laid out to what the efficient span of the panel is, right? It's the beams and girders that are important there. So we don't have to have columns every 10 feet, but we do want those columns on an increment of that efficient span. So 10-foot efficient span for 3-ply, do a 20 or 30-foot spacing for the column grids, and they don't have to be square column grids either. It actually works nicer for vibration when they are not square. So what we're showing here is a 20 by 20 or 30 by 30. I think developers have 30 by 30 in their head a lot. And so this project wanted to meet that request of their spec developer, but you don't have to do it that way. Again, just thinking about the thinnest panel possible and then laying out that grid based on that. All right, I'm going to skip over this particular example and that one as well in the interest of time, and just say, going through those examples that we did, you probably noticed that there's really significant emphasis or focus on panel thickness and really dialing that in or optimizing the panel thickness first, and then laying out the beam spacing and the column grid as a function of that. And why is that the case? Why is panel thickness driving so much of that conversation? And this is a really interesting pie chart. This is from Swinnerton and now Timber Lab, where they're basically saying, you know, if we look at the total cost of a mass timber package, 64% of it is going to come in our material. And that includes the hardware, but the bulk of that, the 64%, the bulk of that is the panels. It's a huge percentage, right? If we think about other construction materials, like a structural steel package, I think that would be reversed. We would see a majority of the cost is tied up in labor to install structural materials. And the lesser of it is tied up in the actual steel materials. With mass timber, it's reversed. So the biggest cost of the project is the mass timber materials themselves. And if we start to look at those materials, the biggest percentage of that is tied up in the panels, the floor panels and the roof panels. And that makes up about 65 to 80% of the total mass timber package wood volume, and fiber costs money. All right, so let's take a look at another example. This is a project that was constructed at the University of Denver, and this information is courtesy of PCL Construction. This project is a 3-story building on a college campus. It's mostly Group B occupancy, and that's the important wrinkle, that there is some assembly space in the building. Assembly spaces are usually one of the most restrictive in terms of allowable heights and areas from a construction perspective. This is a fairly small building, 7,700 square feet. The total building area is just over 23,000 square feet. We're using NFPA 13 sprinklers throughout. The owner had originally requested to have event space on the top floor. Everybody wants to take advantage of the views from those top floors, right? But if we do that, because of having Group A occupancy on the 3rd floor, the building code automatically put us in type 3A construction. So that has an impact on the fire resistance rating of the timber members, the efficient span of those members. Eventually, the design and construction team convinced the owner that what was best to do was move that event space, the Group A assembly, down to the 1st or 2nd floor, because that allowed them to use type 3B construction. What that means is that it's really a cost decision at that point. You know, every design decision is a cost impact. And on this, the type 3A construction 5-panel, that was driving that cost difference. The superstructure cost from PCL construction was at $65 per square foot, versus if they could drop that assembly occupancy down to the 2nd or 1st floor and use type 3B construction, where they ended up using 0-hour ratings to use a 3-ply panel. That dropped the cost of the superstructure by $12 a square foot. So that's a net savings of $250,000 just by moving one assembly into a different space. So that's not always going to be a conversation that the owner wants to change, and that's fine. But if you understand the cost implications of some of those design decisions, you can have those conversations early. So let's get briefly into the connections and the decisions that we've made so far and how that impacts the connections that we use. So we have a lot of different ways of demonstrating fire resistance rating of connections if we need to do so. We can do calculations. We can do non-combustible coverings, so with gypsum. We can use calculations, and we can use actually combustible coverings, like is shown here. These little round dots are wood plugs. So a whole range of options. Structural steel can be covered with intumescent coatings versus steel hardware that's hidden, versus exposed, like that can be allowed in certain construction types as well. So how do we choose the best one? We recently published this index of mass timber connections. There's actually 2 publications here. One's a white paper that provides some background information and then references the actual index of connections. The index is really interesting. We wrote it with a structural engineer and an architect and the contractor. So there's a little bit from every angle. They even have a relative cost comparison of different connections based on their classes. So it's a really useful tool, and I recommend that you check that out. And the fire resistance rating side of connections, I'd like to point out that if you're evaluating a project, and if it happens to be one of the tall mass timber construction types for A, B, or C, there's some requirements in the 2021 IBC specifically related to how we go about demonstrating the fire resistance rating of these. It gives us only 2 options. The first option is testing in accordance with 703, which is an E119 test. That's an option, but I don't think we've seen many of those tests happen yet. And we have lots. We have over 120 tall mass timber projects that WoodWorks is tracking across the US currently. So the alternative to that testing is to do engineering analysis, and those can be hand calculations, but it's more frequently a type of computer model where you're needing to look at, not just does the connection get a fire resistance rating, but also at the temperature profile of the steel, because there's maximum temperature rise that's required.
Now, when they use intumescent paint on connectors, are they painted beforehand, or are they painted after installation, or?
So if you're going to use intumescent paint, use that on exposed areas of connections. Don't then shove it into the mass timber. The way intumescent paint works, and I'm not an expert on this, this is just what they tell me, so take this with a grain of salt. Intumescent paint works a lot like the way mass timber works in terms of, so mass timber, right, as it burns, it develops a char layer, and that char helps to protect it. So with intumescent paint, as it is exposed to fire situations, it expands. That char layer, similar to wood, expands. And so you want to give it room to grow. So you don't want to paint a connection and then shove it in there together. It's not going to work the right way.
Great, thanks.
So that's actually, so when you are shoving steel into mass timber, you're actually using the wood itself as protection in that fire scenario, which actually leads to, I don't want to call it oversizing, because you are using the size for a particular reason, but you are making it larger in order to give it that protection that's needed, whether that's 1 hour or 2 hours or even 3 hours. Did that answer your question?
Yeah, I believe so. That was from Cliff Marvin.
All right. So we're going to end here pretty soon. I just wanted to touch on penetrations and fire stopping. This is coming up more and more as these mass timber projects are done. Of course, this relates to construction type and fire resistance rating as well, right there in the code. From a code perspective, the options are, if we have a through penetration fire stop system listed in accordance with ASTM E814, we're looking at F ratings and T ratings depending on for just walls or walls and floors. We do have some options that have been tested through penetration fire stop details, and we do have those in our fire tested assemblies. In that consolidated document. I will say that the general rule of thumb or general construction makeup of these is that it's some combination of fire safing materials. Mineral wool insulation as a non-combustible insulation material is pretty efficient at filling the annular space between whatever the penetrant is and the hole in the master panel. And then usually some type of fire material, like a fire stopping detail. It's not just fire caulk, but it's a fire stopping material. So it's acting as one system. And so whether you're referencing someone else's tested system or you're referencing an engineering judgment detail, we see that time and time again in mass timber construction, where a lot of the manufacturers, they haven't done the tests yet, but they are willing to write you an EJ. So those inventory is also in that fire tested assemblies mass timber document on our website as well. Oh man, there's just so much to talk about. Here's one, I just really want to pull this out. So if your fire, it's why it's so important to start right at the top of type of construction. If your type of construction is, say, 3B or 5B, where you have a 0-hour fire resistance rating, then you get to just analyze a structural impact of a hole. Like if you're going to be penetrating these systems, you just get to analyze the structural impact of that hole only as it is. But if your fire resistance rating is not 0 hour, if it's above that 1, 2, 3 hours, then you have to account for the charred hole diameter or the fire stop penetration. So you know, it might look like this in the field, but in a fire situation, you have to consider as the engineer what that hole diameter is going to be, and will that fail the beam or not? So what looks like a little hole might be a really big deal, which is why this picture is actually taken in a project that is a type 3 project, a type 3B project, which has a 0-hour rating. All right, I'm just way out of time here. And so I think this is actually my favorite part, but we're gonna skip it. And if you would like to see any of this, if you would like to have me do a presentation for your firm, if you're interested in MEP or things like that, we have a great webinar on this. I'm happy to come into your office virtually or otherwise and talk more about it. So instead, I'm just going to skip us right to the end here. And for key specification and building envelope resources, I want to give you this list. The first is our US Mass Timber Construction Manual. It's available for free download. It has a great chapter on moisture management. I would look at that. Also, RDH has written really good 2 mass timber documents that are available for purchase at learnbuildingscience.com. The moisture risk management strategies for mass timber buildings, and then the building enclosure best practice design guide. Those are 2 really good documents. I recommend you get those. Every manufacturer, mass timber manufacturer, has their own specifications. WoodWorks is working on a mass timber specification that is supposed to be generic. We're still working on that. Hopefully that'll come out this year. I wanted to pull out, especially when we're talking about moisture and construction, the Canadians have been doing this for longer than we have, but on some of our mass timber projects, we're starting to see more owners interested in a monitoring technology. And so SMT has a system specific for mass timber. They do have a specification for that as well, if you'd like to pull that out. Also, AIA Seattle Mass Timber Committee, they have a moisture management working document that they are updating. So look for updates later this year on that. And finally, I'd like to encourage you all who've done your first mass timber project to market your experience on the WoodWorks Innovation Network. We'll give you a boost there. And then with that, I'll take any questions, or we can hold questions for later. I'm happy to stay around as well so that we get to Richard's talk.
Great. Janelle, we did have a question about exposing mass timber to the elements. Is that ever appropriate?
So I have a lot to say about that. I'll keep it brief. First of all, the ANSI APA PRG 320 document, that's the manufacturing standard, does not it specifically says that it is not for wet use. So it is not for exterior exposure. So be careful if you want to expose it, that you're not voiding that standard. Secondly, if the places that I've seen it exposed have been protected areas like soffits. That's a popular one, to expose it in soffits. As a building envelope engineer, I would caution you to just be aware that mass timber, while it is a vapor barrier in and of itself, it is not an air or water barrier. So just remember that, especially from an air barrier perspective, right? That you are breaking your air barrier right at the soffit of your roof. Do you really want to do that or not? I think we get stuck as designers in seeing all this beautiful exposed wood and absolutely do that on the interior of your project. But please, please, please treat your buildings, your mass timber as structure, because it is. It's beautiful. You want it to stay that way. You want to protect it from moisture, which is no material's friend, right? Least of all woods. And so we see all these great things that look like wood, but actually aren't wood on our facades. And we get kind of sucked into thinking that that's real. But on a lot of those things, we're actually seeing the full air barrier, moisture barrier, water barrier design elements, and then it's covered with a replaceable wood element that looks like mass timber. So please, please protect your structures.
Is the NLT and DLT also a barrier? You said it was a vapor barrier? Sorry.
Yeah, it's so much wood, right, that it sort of acts a lot like a vapor barrier, but is definitely not an air barrier. And it's, man, CLT is not an air barrier. DLT and NLT are really not an air barrier, with all that grain running in the same direction and all of those, joints between the two that are only mechanically fastened together. RDH wrote the building envelope section for the NLT guide. I would highly recommend checking that out if you're doing an NLT structure as well.
Okay, great. I'm not seeing any more questions in the question and answer section, but I will try and open up the conversation so that everybody can actually chat at the end of the presentations. So if you guys want to stick around for that and be able to kind of say hi to your colleagues, that would be cool. So now we're going to hand it over to Richard Green with Green Facades.
Thanks, Janelle, for that fantastic talk on mass timber. And I've learned a lot, and we're certainly seeing projects out there. So it's great for all of us to know how we're interfacing with this product and how it actually affects how we're attaching at the edge of buildings, and connections for the facade systems is also interesting. And perhaps that's something we can talk about when we get to question time at the end of it. I'm here to talk about glass today. Quickly, for those people that don't know Green Facades, it's been around since about 2001 in Australia. I took an interlude while I was the principal and technical director for Front. But Green Facades has delivered projects across USA, Europe, Australia, and Australasia. We're a full service facade consultancy with system design, structural engineering, and building science, and we're based in Seattle. So projects of all sizes, airports, sporting facilities, interesting geometries, and interesting uses of glass around the world. So curious, are you getting these little side screens of people as it's being reshared, or are you just getting the presentation? It's all good? All right.
Yeah, it's all good.
Excellent. So as I saw a need for people to be able to design more confidently and more freely with glass, founded a technical group with ASTM to do structural glass. That's about 10 years ago, and a number of years back, I did do a presentation for CSI and describing that work. We got to the point of having a first draft, and it's a very useful document, but it's currently grinding its way through the consensus process where people are interested in the economic implications as well as the wording and the form of the document. So in the interim, what I'm doing is spreading around some of the information that's been developed over the past 10 years. And to that, I want to thank all the people that have participated in that. But I would say that what I'm sharing here is very much my personal opinions, and people are welcome to talk to me about what is appropriate. So talking about Windows, part of the reason we are where we are is because the technology has grown over the years. And when we start with Windows, we started off in the Georgian period where we had spun glass, basically glass blowers, and they'd cut out these square pieces of what they could cut off the disk. And we started off with these small windows. And for the benefit of transparency, breaking was the price we were prepared to pay because it was so small and it had virtually no implications. Come the earliest 20th century, and we start getting into full height glass walls. And this is one of the first all glass curtain walls in San Francisco around 1920. And of course, now our glass towers, we're using four-sided supported glass, floor to ceiling. And this is pretty common, and we're still in the situation where we say, we're comfortable with this, the implications are not significant, not serious, and we're very happy doing it. Well, then we get to the point of having bigger glass walls. And here we're at a scenario where it's about 20, 24 feet tall, but it's supported off structure which is independent, it's not glass and it's not brittle, and maybe one unit could break and the occupancy might be limited. So we're starting to get further up the spectrum of significance of how our glass is being used. Well, we also have glass fin systems, and now we've got a wall which is a little bit taller again, and it's actually relying on the glass to hold the dead weight and hold all of these different units together. This should be at the point where it's starting to pique our interests as to, should I be thinking that this is something special? Because at this point, according to IBC, we'd say it's a vertical glass wall within 15 degrees of vertical, and we don't need any retention, redundancy, or lamination by code. Okay, but things happen, okay? And the interesting thing with glass is the things that break glass usually are not the design loads. Okay, so when we talk about a probability of 8 in 1,000 or 1 in 1,000 or a 50-year wind or greater, we've usually designed for that, and that's usually not the thing that breaks it. It's usually an imperfection in the glass, a manufacturing defect, an impact, or something which is not part of our design scenario. So we need to take account of the fact that glass is brittle, and when it cracks through the entire ply. But we can design it in such a way that is reliable, and that's our choice. And so the real crux of this matter is we've got choices between glass, which has been used for a long time in an unlaminated or an unrestrained form, and glass that can be fully robust, and when should we use what? So here's an example of what we think of as a fully tempered wall assembly. And we need to start thinking about, is this an appropriate way for a system to fail, right? So as we look at this and we talk about it and we say, fully tempered glass breaks into small dice, is it safety glass? So as we look at that frame by frame through the process here, we've really got to start questioning, if this chunk hit you, would it do some damage? And the answer is the cracks propagate through the center of the glass where there's a tension zone, where it was put into compression on the outside. The cracks don't progress through the compression, and it holds together until it hits something solid. If it's the ground, great. If it's a person, it still has the capacity to do significant damage. Now, the place where we see this most often is in shower recesses, where we have fully tempered glass with unframed edges, and when it breaks, it holds together in pieces until it hits something. Okay, so we see these big chunks falling, and they're being held together by the skin on the fully tempered glass until it hits something. And even in the end, there is a piece still hanging there because of this skin and the mechanical interlock in the systems. So when we talk about safety glass, does this have sharp shards when it hits the ground? No, you can pick it up with your fingers because of the dice. But is it something you'd want to get hit with? Think about how and when you use it. Now, let's move on to the next slide rather than... All right. Now, the other extreme, this is the floor of the Space Needle. This is the opposite extreme of robust. And so it took 6 really good hits with an Army drill sergeant glazier, and you can still stand on it. Okay, so these are the extremes of what we have in our design spectrum of glass. Okay, and what I'm going to try and present to you is a way of thinking about what is started off as something very familiar. It's grown, it's grown, and it's grown. And we eventually get to a point where our rules of thumb of what is okay needs a quantum change in the way we think about it. And then we have the ability to do amazing things with it. And sometimes there's a cost implication with that and how we think about the spectrum. So, you know, there are implications of doing it wrong. We think about small skylights. People don't walk on skylights. Well, are you in an environment where people are going to potentially trip because they're in a snow environment and not realize it's there and fall onto the skylight? Are people going to potentially access a space where they weren't intending to be there? Is there going to be a person that's going to be up there because it's a large skylight and they say, can I walk on the glass to look at the lighting system? And they're told it's okay, only for it to be inappropriate. So the degree of redundancy that we build into systems, can we? Yes. Should we? Sometimes. Do we always? Definitely not. In the 2015 IBC, we started talking about glass balustrades because pieces of them kept on falling off. This is a classic case of glass that's fully tempered, has potential imperfections, has no perimeter frame, and when it breaks, it falls. Now, since 2015, enough of these happen that you must laminate your balustrades. Okay. This is a step in the direction of codifying safety in glass. And we might get a chance to talk a little bit more about balustrades, but let's talk about windows for the moment. So there's a risk is the probability occurrence multiplied by the consequence. So for most materials, we just talk about probability of occurrence because the outcome is ductile and it's predictable. But for glass, if it's glass on its own, the outcome is less predictable. And so we need to think about not just the probability of breakage, but the consequence should it break. We also need to add into that the glass breaks from causes in addition to the design load: impact, nickel sulfide, imperfections, air bubbles, construction damage, etc. And so we need to consider the occupancy. Where's it going to be? How's it going to be used? Will there be people there? Now, if we look at the ARMA documents, they'll say, let's take the probability of failure from 8 in 1,000 down to 1 in 1,000. Reduce the probability of breakage. But does that make it safer? Once you initiate a crack from the surface, probably not from the design load, that crack propagates through the full ply thickness. And so, have you made it safer? No, you've made it thicker, you've made it more expensive, you made it heavier, and you've actually made it more dangerous if or when it falls. So just reducing the probability of failure to the design load is only part of the story. What we need to do is control the failure mechanism. And for this, we start thinking about robustness that comes through redundancy, retention, and residual load. And that's the way all structural materials think, except that window glass, we've been so used to not thinking about those parameters. So structural glass is absolutely possible in the same way that we think about reliable design in other materials, because we have the technology and the lamination materials to do that, but we don't always think that way. So this is a way of thinking about the spectrum and what we can do and what we should do. So looking at the space, beautiful big glasses, potential crowd loadings, restraining people from a 500-foot drop. This is clearly a special case, and it's designed with great degrees of robustness appropriate to it. So why do we need a design guide? Glass has capacity. In compression, it's one of the strongest materials known to man, but it has no ductility, and fracture mechanics control its strength. Heroic designs have been done, but there are also some poor ones. And we've got to be careful about not just saying we designed for this load, therefore it'll be okay, because other things happen to glass which can damage it. Now, until we get a glass design that can be a glass design guide or standard that can be specified, until that time happens, we need to build this into the specifications, the project specifications for our projects, and think about it as a design decision between the architect, the owner, the engineer, and the contractor. And just like Janelle said, the sooner we get into that process, the better the outcome is going to be. It's very important to get people in early when you start thinking about using glass in non-standard means. So until we get a standard published, we are the people that need to be thinking about how glass should perform, and it's our choice. Interestingly, we see people taking conservative approaches where it's not necessarily necessary either. For example, people are specifying hurricane glazing, which is missile resistant in New York, because they want to control the failure mechanism, and those are the only ones which are standardized at this point of view. So that has a cost associated, which is potentially more than is appropriate. Let's have a look at some of the spectrum. At one extreme,
Can I ask a quick question, Richard?
Yeah.
Is there a method to design glass like another brittle material that we've designed for a long time, concrete? I mean, there's rebar design that goes in concrete to control load. Is glass done the same way with inner layers?
You're thinking in the right direction. Okay, so if we were to look at that floor with the sledgehammer, that is behaving like reinforced concrete. The glass is acting compression, the interlayer is acting in tension like the steel, and it forms a composite beam like the same way. It's difficult to compute and the research is not as strong as it is in concrete. So there are 3 different methods which we think about in terms of restraining concrete, that's restraining glass. The typical one is 1-ply broken, which is what we see in E2751, and that's the glass floor standard. And it says with 1-ply broken, you should still be able to support the design load with no further breakage. Now, the glass, we just say it should take the design load, but if it breaks, it can fall out. In the seismic section of ASCE 7, it says if we shake the building around, it should not break the glass in such a way that it falls out. Okay, that's the one sort of spot where it says glass shall not fall out. But other than that, and if we get down in Florida and the hurricane zones, then they have also considerations for impact resistance. But generally for vertical glass, we say, okay to fall out. Floors, we've got a variety of things. One is the fully broken case, which you say like reinforced concrete. Safety films are an option, laminations are an option, and catch fittings. So there are different ways of getting there. And what I want to say is we should be thinking about the performative outcome, not the prescriptive outcome, unless as a team we are choosing a route to go down.
Okay.
So I'll go down some more of those options as we come forward. Okay, so I think I actually covered this one. This is kind of like our 2 extremes. In between, we're going to have all these other options of how we get suitable failure mechanisms if we get damage so that we don't get outcomes which are disproportionate to the event that causes them. So looking at this project, something's missing, okay? So this was a project where it was a fully tempered piece of glass. It had nickel sulfide inclusions, spontaneous fracture, the edges of the glass is unrestrained, and the glass evacuated the opening as soon as it broke. And in fact, as the glass expanded with a crack wavefront, it jettisoned glass into the floor above, into the 1/4-inch thick aluminum post, and fell in chunks over these 3-4 floors till it hit the ground, got scooped up, got put in a green garbage bin, got laid out on the ground, and still had pieces as big as an 8.5 by 11 comp pad. That's not what you want to have hit you thinking that it's safety glass. So thinking about outcomes. So the aim here is to provide good design principles, give you some ideas of how we can do it, not limit the way that we advance designs in the future, and say we want a principle, not a prescriptive outcome. Have a way that we can advise the authorities to evaluate the designs we're preparing to say that we have achieved good outcomes so they don't get nervous about it. There are certain jurisdictions, Seattle's not too bad, they're very thoughtful about what we do. But if you're working in city of LA, city of Long Beach, Miami, Chicago, or Portland, Oregon, I know we've got some Portland people listening in, they are very interested in how the glass is behaving. And if they don't see something to a standard or to a design philosophy that makes sense, they will make you go out and test it. And the testing is very expensive. So we want to provide them with a really strong narrative of how we've designed it, why we've designed it, and why it's the right thing to do. And so if we get this balance right, we get safety, we get robustness, we can do heroic things with glass, and we can think about what is cost appropriate. So will a standard for glass look like a typical standard? And the answer is no, it's not ductile. We can't rely on it to bend to give us warning of what's going on before it starts being a problem. Unlaminated glass, or glass without a safety filament, has no warning of potential catastrophic failure. But there are applications where it's been used widely and successfully. And in fact, 90-something% of glass falls into this category of widely and successfully used. But as we get bigger, as we start going beyond the bounds of what's been traditionally used, we need to be thinking about how we're using it. And that's what we're talking about today. So here's my 7 R's of structural glass design: risk, reliability, resistance, redundancy, retention, residual capacity, and regulations. Circumstance and consequence is a really good thing to be thinking about here. What's the location? How high could it fall? Is it going to be supporting somebody with live load, either because it's publicly trafficable or through maintenance? What's the orientation? If it's less than 30 degrees from horizontal, people can get on the glass. If it's more than that, they're likely to be in a full arrest system or have a ladder or something else on top of the glass that will stop them going through it. So the orientation and its application. Why is height important? Well, I could design a piece of glass and it's just at floor level. And if it only falls 10 feet, it's not really a problem. But I could take exactly the same piece of glass, put it in a hotel atrium, 100 feet up in the air. And if that falls from that position, it's got a very different consequence. So here's 2 systems. They're glass fin systems. One is a standard office lobby. One is the famous Apple Cube. But if we compare them by size, they are completely different in terms of what they need. And so the piece on the right is heavily laminated. The piece on the left probably isn't. We spoke earlier about probability. Just 8 in 1,000 or 1 in 1,000 is not enough. We need to consider the other risks that may be in there, accidental damage and what place they might have. Now, IBC does talk about accidental damage, and there are some load cases, particularly from the 2005 version, that talk about wind loads. After that, they talk mostly about dead loads because they're thinking about accidental damage from fire, explosion, and vehicular impact. All of those things are still real risks for glass, but we also have these additional risks such as nickel sulfide, inclusions, hard body impact, installation. So I think the classes that we need to be thinking about come into 4 different ones. Glass risk category 1, glass usage that represents a low risk of injury in event of failure. And these are the ones which were probably really common and what we're used to: residential, standard windows, etc. G2, a lot of these are also the standard applications, but you're into the point where you're starting to raise the question of, should I be thinking about something special here? So for G2, a lot of the applications are similar to G1, no specific requirements, but they start giving some guidance to when we should start be thinking about retention and redundancy. G3 would be thinking about this as being an enhanced version. Maybe I don't need the glass to be retained, but I'm in an area where I might have higher occupancy and the consequences of failure could be greater. Therefore, I want my glass to be retained. Or I'm in a commercial facility where disruption to having to blockade off an area because of a damaged piece of glass would cause either economic or functional challenges. G4 is what we like to think of as essential. You can have impact, you can have damage, but it still does its job. This is a bit like hurricane glazing. It's got to do its job. So G1, we start with either very low occupancy, here a greenhouse, or residential, some standard storefronts. And this happens to be a car dealership across the road. And I was just going, oh, this is a nice example of it. And then I look around the corner and just go, well, that's interesting. Is that by design? And then I found the little slug shots in the laminated glass. So I now know that this has actually been designed as a G3 type assembly, but it could have been designed as either G1, G2, or G3. But it's kept people from entering the Jaguar car showroom here. So interesting. G2, standard occupancies, getting bigger, not necessarily a high occupancy lobby, but it's a point where we want to start making it safe. When we start getting into 3, high occupancy, things like concert halls, stadia, public facilities, downtown areas with lots of people around it. Airports, here, Bangkok Airport, or things where it's got a critical function or an essential function. Even if something breaks on these barriers at the Seattle Space Needle, it's vital that we don't drop a 3,000-pound piece of glass 500 feet, and it's important that the people behind it also are safe at all times. Now, depending on the location of the project, we might say a standard residential window has critical function. So if we're in Florida and something hits the window and it causes a breach in the envelope, that can cause pressurization of the building, loss of the roof, and then collapse the entire building. So in this application, this would be a common usage of a G4 type glass where it has a critical function after damage. So having looked at the occupancy of the building, and we start going from virtually unoccupied, standard occupancy, highly density, or essential, then we start thinking about the circumstance and consequence. And this will then give us a guide to how much redundancy or retention are needed and what are appropriate loads. First thing to consider is this an infill piece? Is it just like a window or a balustrade? Or is it like a glass fin, secondary structure, it's supporting something else? Or a primary structure, perhaps a glass shear wall or a glass column that's holding everything up? So the question is, does it support other things? If we lose this element, do other things fall down? So it's usage. Orientation, are people on it or under it? Definitely a consideration. Barrier, does it have a safety requirement? Do people need to, does it stop people from falling? And is that requirement just a singular impact, like somebody slipping into it in a residence, or is it potentially a crowd situation where people could continue to be pushed, such as a school, an atrium, an auditorium, or a sports stadium? And floors, public live loads. So to your question earlier, Beth, here's some of the ways that we might want to think about it. We start off with no requirement, then we get to it just doesn't fall. So it could have a safety film on it, could have a screen underneath it, something that stops the glass dislodging, swinging through where it can hit somebody. Are we going to fully retain it in its space, which could be either one ply broken, all plies broken like the reinforced concrete? Or are we going to say this type of assembly just isn't appropriate in this location? So set of tables have been developed, and one of the current things that's holding up this getting published is trying to get the simplicity of this document to a point where people can approach it. So G1's pretty simple. It says basically if it's an infill that's vertical, there's no requirement, and we don't want to do unreinforced systems for primary structure, so it's not permitted. And there's a little bit in between. And simple cases, as we look at sort of G1 into G2, would be an office block. And this is one which I did a while back in Melbourne. Or getting a bit fancier, this is the Sydney Hilton arrival court with a glass wall and redundant glass fins in it. And so as we look into G2, we see, again, if we're up to 18 feet, really no requirement if it's vertical. But as we start getting into systems which have greater complexity, greater reliance on them. So this is our safety one, and we say if it's four-sided support, no requirement across the board. So we haven't changed the world here. This is our standard curtain wall systems are still in play. But as we start getting from infill elements and start getting into stacked glazing systems, we need to start considering what happens if we break one ply. If we start getting into glass beams, then we start thinking about, okay, we want to talk about 20% of the design load maybe, and saying that's the accidental load, which comes from SC7 for accidental cases. But it's also a way of thinking about it and going, if we have a 2-ply laminate and we break one of those plies, then we've got about a quarter of the strength left. And if we're designing for 20% of the load, it shouldn't cause us to upsize. It should just be a nice, sensible design of about the same thickness, but laminated. And so we start seeing things which are trying to have a practical post-damage design load that leads to outcomes that are not commercially ridiculous. Then we get through to primary systems and we say, like 2751, 1-ply broken should still take the design load. Or we take the all plies broken, just like the reinforced concrete model we were talking about earlier, that can still work. That's also okay. Or the load could go to an alternative path. And I'll show you an example of how that worked as well. So as we move into G3, we start talking about transit centers, places with higher density of people around it. And again, if it's 10 feet, not really a concern. Once we start getting to taller areas, even our curtain walls may be still appropriate. But we start seeing now no further breakage with 1 ply, a little bit more load, no fall. That would mean if it could leave the opening, but a safety film holds it in place, or it's retained with all plies broken, the reinforced concrete model. So there are options on how to do it, but basically the idea is the glass doesn't fall on anyone in G3. And it goes through and it looks at lots of options, lots of scenarios, and provides guidance for what is appropriate for each of those scenarios. And the important thing here is the designer gets to choose one line, which way he wants to design it. And it's a bit like ASCE 7 in the seismic requirements, where he says, I've got a whole menu of how I can design this structure, and I'm going to choose which one I think is most appropriate. So here there's options and it's performance requirements, not prescriptive. Bangkok Airport, G3, then we get into G4. Maybe even airports are essential facilities. They must continue to function afterwards. So we get into G4. And this is where we say it needs to have a residual capacity even with all plies broken. So here's the takeaway from it. G1, it's basic. There's limited risk. This is what we're used to seeing. G2, it's good. It's typical. We've defined where the safety risks start kicking in and where you might want to start doing something a little bit special. G3, the client says, I've got higher occupancy or I don't want disruption. And so this could be thought of as enhanced capacity. Or G4, it's just got to stay there and continue to do its job. It's essential. doing a quick time check here. 6:45. Oh yeah, we've got a little bit of time left.
We did have a question about the impact of chemical tempering used in these designs. Is that applicable?
Right. Yeah. Chemical tempering or chemical strengthening can give you some really strong glass. And what it does is it does an ion exchange, but it basically puts bigger things into the surface of the glass and generates a very, very thin level of high compression without generating a complete body of tension in the middle. So as long as the surface doesn't get damaged, it can sustain very high levels of applied tension, which is offset by the compression, and you end up with a net tension. Okay, so net tension on the surface is what actually causes the fracture to grow. Net tension is the applied tension minus the residual surface compression that was already there. I'm getting a little technical on here, sorry, but I hope you're following. Thermal tempering gets it to a level of compression, let's call it 100, which is generally in about 100 MPa if we're thinking metric. Chemical tempering, about 6 times that, stronger, but it's very thin. And the risk is if you scratch it, you could go through the level of compression and expose the unstrengthened core.
So it makes it stronger, but it fails more spectacularly. Is that what I can translate that as?
It makes it stronger before it cracks, but when it cracks, it still propagates through the entire ply. And because there's not tension in the middle, it tends to behave a bit more like heat strengthened glass, and it goes into big pieces rather than the small pieces that you see with fully tempered, which has a lot of energy in the core of the glass. So less spectacular, but
bigger shards.
Bigger, more dangerous
big pieces, more like annealed to heat strengthen in the way that it fractures, but it happens at a much higher level before bigger loads before it happens. And it's the energy from the loads which cause it to be a bit more exciting when it breaks.
Thank you.
Okay. Use it.
So the answer is it's really strong, but it doesn't control the failure mechanism. Okay. So the thing which I'm going to tell you here is it doesn't matter how strong you make the glass. Once you initiate a crack, it goes all the way through. And if it goes all the way through, you've got to start thinking about how does it break. If you've got a laminated piece of glass, it's a bit like your car windscreen. You get a crack in one piece, it gets a crack through it, but it still stays there and does the job. And some of us leave it there quite some time. Okay, generally because it's on the compression side, it's okay. We're thinking about how it works. So the real message here is thinking about how we laminate it, not how strong we make the glass or what the probability of failure is. Okay, so G2, limited detachment. It's okay because there's generally not going to be a person there, or we've only let it fall from a limited height, so it's not going to hurt them too much. Okay. Starting to move into G3, can be characterized as there's some risk of a person being near the glass when it dislodges. Therefore, we try not to let it dislodge, because if it did, it could present a risk, either economic or human. And so it has some degree of post-damage capacity, but not necessarily full capacity. So looking at sports stadia, this is a glass roof. Do you get to see my pointer on the screen as well?
Yes, we do.
Great. So this is a laminated glass roof 100 feet above the stadium, which holds about 120,000 people. You don't want that piece of glass to fall down, so it's fully retained in location. Glass for risk category 4, essential facilities. Doesn't matter what happens to it, we want it to continue to do the job. So things like the glass floor at the Space Needle, if somebody drops something on that, we don't want that piece of glass to fall down. So the engineer's takeaway here is when the guide comes out, it'll give you a clear definition of what is required when. In the interim period, as specifiers, we should be thinking not just about, is it going to be safety glass? Is it going to be vertical? Is it going to be inclined? But should it be laminated? And if it's going to be laminated, are we just going to say, oh, because it's laminated, it's okay? Or are we going to actually put a performance requirement on it, which says, as the glass gets bigger, maybe the thickness of the interlayer proportionally needs to get bigger as well. And so it needs a performance requirement, not just saying 060 PVB is going to be fine. And we start seeing this in balustrade performance as well, where people say, if we're using stiff interlayer, it's going to be better. People are starting to think about what is appropriate for post-damage condition, post-damage performance, post-damage loads. So if we took a quick example, how does it work? Here we've got example with a point fix, it's vertical. We're into this area. We're going to choose a path to the fin. We're going to say, assume that one ply is broken, no further breakage with 20% of the design load. So we see here this 0.2 on the variable loads. That's how we'd go into the table and choose what we want. There's a variety of retention options. We've spoken about the lamination, anchored films, catch screens, because this is not the outcome that we're looking for. Yeah, this is where the hurricane glazing started coming in. And incidentally, this is not from the glass being under-designed. This is because there's a building off screen to the right-hand side of the screen here, which had an inverted roof with ballast on it. Nice small pebble ballast, which gets picked up by a hurricane and thrown against the glass on the adjacent building. So impact resistance and its behavior there afterwards is important. Okay. Different type of retention here. This is the Changi Airport in Singapore. As we're designing this, we're saying, please don't design point fixed, fully tempered glass without any edge restraint, because if we get nickel sulfide or anything else that causes a break, it comes down immediately. And they said, no, it'll be fine. We've got online heat soak testing that will take the risk virtually to zero. Well, unfortunately, it didn't work. And the nickel sulfide continued to cause spontaneous fracture, and it did come down immediately. And so this got a safety film on it, which was anchored to the pucks, and you can just see a little bit of the adhesion to the puck there. It was tested, and this was a way of retrofitting the retention of the glass in an internal environment against the risks of internal imperfections in the glass. So redundancy, we get it through lamination, number of members, or alternative load paths. So this is the Flemington Racecourse. You can see here that we have a grandstand, and like most grandstands, they don't want to interrupt the views, which means there are large cantilevers. The difference between this being fully loaded and it being unloaded is about a displacement of 2 inches in the edge beam. We want to have a glass roof so we can see the view. And we can't cantilever that out because that would be a lot of weight on the structure and torsion on the edge beam. So this is designed as the glass wall holding up the glass roof with a steel fin system in between. But the way this works is if we get damage to one ply, the other ply takes it in the lamination. If we get damage to 2 plies, the adjacent unit takes it. If you get damage to all 4 plies of these 2 units, then there is a bump stop on the pivot of this girder, which means that the edge beam of the structure takes the dead load of only these 2 panels of the skylight. And if you start losing more than 4 panels of glass in here, you've probably got an event which is sufficiently severe, then you're worried more about what's happened to the people directly than what is the collapse mechanism of the glass. So the story here is, think about keeping the consequence proportional to the event and keeping it sensible. So unfractioned design, design it so it doesn't break for the design loads. Good for most of the time, doesn't account for random failures. Think about fraction design. What happens if you lose 1 ply? These random failures tend to be 1 ply at a time, and they tend not to be coincident with the design loads. And so we can think about it as what happens with 1 ply broken. And this is what happens in our this original test case that got it started. This is First and Main in Portland. This whole process got started with the building department going, we don't have a standard for glass fins. We don't have a standard for glass with holes in it. And we are naturally concerned about the way that glass breaks. Well, this was designed as a 3-ply laminated glass fin. We tested it. We convinced the city that it was all good. And as it would happen, there was a nickel sulfide imperfection in the fin, and we knew how it would behave should it happen, and it did exactly what it should do, which is to stay there. And it continued to have capacity, 2/3 of the capacity, in fact. And because we generally have a factor of safety of 1.5 to 1.67 on our wind loads, between 1 in 50-year loads and ultimate loads, this was actually still adequate for a design load, and they could keep the facility open until a replacement fin could be procured.
Richard, you said the
Yeah.
loss of 1 ply in a 2-ply system was more than half, but with a 3-ply system, it's still 2/3.
Right, so here we've got, if we've got 2 plies which are next to each other, they have a strength, and I'm loading downwards, like think of a stair tread. When I lose, the strength of that's proportional to the square of the thickness. So if I lose 1/2, I'm down to half the thickness and 1/4 of the strength. When I'm acting parallel, so this way, and the force is in plane, then when I lose 1, I've still got half the strength. If I've got 3 and they're acting in plane and I lose 1, I've still got 2/3 left.
Okay, so it's the
So it
orientation.
depends on
that's
which way
different.
it's loaded.
Okay,
I hope that makes sense.
yeah, definitely. Thank you.
But, and in fact, in this case, it was the center ply, and it was like held together by the 2 pieces. It probably had more than 2/3 of its strength remaining. But this is like the difference between that collapse mechanism I showed you in the video earlier, where multiple chunks of glass start falling down because it loses its dead load support, and something which is a complete non-event where, okay, it's cosmetic, it went bang, it's exciting, people have got to fix it, but it's a 0 risk event. And this is where some design and thought about how the system works can really change the outcome to these rare events. So takeaways: non-structural, limited consequence, continue doing what we're doing, E1300 applicable. Structural, it's got consequence, it's got job to do, even if it gets damaged either by design load or non-design loads. Glass can be designed like other structural materials, like reinforced concrete. It can be forced to work in a ductile manner, but generally we don't. And there's a spectrum between full design and non-structural design. And that comes into the idea of partially damaged and partial loads based on the conditional probability of what load happens between when a non-design damaging event and when you replace it. So let's take that glass fin we just saw on the previous slide. Let's say that it takes 3 months to procure and fix this fin. That's not a 1 in 50 year design load. We probably design that for an annual design load, and that's why it's 20% wind load, not the 50-year design load. I hope that makes sense. So conditional probability in the damaged state. We have the technology. Size matters. When it gets really big, we start the rules of thumb of retention, how much interlayer should be in there, how we design it, needs to be starting to think about it. And as designers, we have the choice. And because we have the choice, we also have the responsibility to think about these things. And of course, when you put all these things together, you can do wonderful and heroic things. And so I hope that as we've gone through this discussion, I don't want to scare the living daylights out of you for using glass. What I want to do is say, we can use glass in incredible and wonderful ways and be confident in our design because we can think about how glass is designed and we can control the failure mechanisms and we can make it behave appropriately. And when we do that, we can do great things. Thank you. All right. Have we got any other questions?
Richard, thanks so much. I have not seen any other questions in the Q&A field, but if anybody has questions, please do write them up.
So as a structural engineer, I went to school for structural engineering, and there's a big fat manual for how you have to design concrete and a slightly fatter manual about how you have to design steel.
Mm-hmm.
So you're saying that doesn't exist for glass?
Correct. So
that's terrifying.
Yes, and the counterpoint to that is when we wrote a big manual, people said it's too big, you've got to start small and let people let it grow. And the problem with doing a consensus document as opposed to, and this is part of the challenge of working with ASTM, which is a consensus document, as opposed to, say, ASCE, which is we put a bunch of engineers in the room and we say, does this make sense? Is people don't necessarily want to see comprehensive at the moment. And so I'd hoped that we'd be like a year away from having something published. People are saying, well, we've got a window standard, and we've got a floor standard, and we've got a balustrade standard. That seems to cover 90% of the job. Why don't we just leave it at that? And then I sort of say, well, but what about skylights? And people say, people shouldn't walk on skylights, but people do walk on skylights.
There's all kinds of stuff people shouldn't do. And yet.
Right. And you talk about canopies, people say people shouldn't be on canopies, yet in building code in Melbourne, where I come from, canopies actually have a crowd loading imposition on them because when people have street parades, people actually like to congregate on the canopies, right? Because that's where they get to see stuff. And so it's not just a maintenance load on canopies, it's actually a significant impost load for canopies that are less than 10 feet high. So what I want people to be thinking about is, we could equally be talking about balustrades. Well, balustrades, we have this idea of, okay, we've got a rail over the top and we have an infill piece of glass that sits between them, or sometimes we have just a cantilevered piece of glass with no rail across the top. Well, that in an unlaminated form has been outlawed by IBC 2015. And the reason for that is you get spontaneous fracture, it was falling down on the street and it was a risk to people. Mm-hmm. But what it didn't also address is if it departs the opening and it's a residential situation and the mum opens the door and the toddler wanders out there and is used to being able to press against a piece of glass, well, they don't see the opening and they don't perceive the difference. And they unfortunately have wandered out and just crawled off the edge of the balcony. So we don't want spontaneous departure from residential. You know, there are other cases where people are leaning against the glass balustrade and they drop their highball glass on the top edge, and fully tempered glass is vulnerable to edge impact. So then they're leaning against it and they're out over the edge. The biggest situation is crowd loading situations, because there, not only is it the one person that might be leaning against it or the person that slides into it and hits it, which is the impact test that we do for balustrades, but you might actually be in a situation where something causes the balustrade to break and then the crowd continues to push the people behind it. And I have a video. It's amazing what happens with people having their iPhones these days and the things you capture, like that wall collapse earlier. That wasn't a premeditated test where we happened to put a camera in place to watch it happen. That's somebody's iPhone going, oh, I hear something going crack bang, and it breaks, and then we then get a record because it goes viral. There is a case of a steel balustrade that has a brittle failure, just like glass would have. In a school situation, there's a crowd there and they're not being particularly, it's not like there's Justin Bieber on the center stage of some shopping mall and everybody's pressing to see it. It's just a crowd of kids there. And there's a bit of jostling going, but unfortunately, 7 kids go over the edge, because not just the first one, but everybody's kind of like pushes against the next row of people. And so when we start getting into crowd situations, we start thinking about not just the initial failure, but the capacity of the unit above and beyond when we get into those situations. So even as we start thinking about the way ASCE 7 works, and we work with 50 pound per lineal foot as the design load, if we were to look at other parts of the world, say European standard, Australasia and the Australian standard, they would have also 100 pound per foot, double that load for crowd loading, and 200 pound per foot for crowds with crowd surge loading. And so our initial loadings that we have here are really pretty light in the scheme of things. And at the moment, all it says is thou shalt use laminated glass. It doesn't define what the capacity shall be for any situation. And it treats all glass as having the same requirements regardless of the occupancy that's around it. And so I think that there's, the big thing to take away here is it might be okay in a residence. It might be okay in a typical office lobby. But when you start getting into auditoria, when you start getting into crowd situations, when you start getting into crowd surge situation, you can't design them the same way. Even though ASCE 7 says they're the same load, even though they're the same height, even though they've got the same load attraction area, we need to be thinking about it in terms of the context of our buildings and designing them completely differently.
We did have a question from Cliff about asking if the FGIA is involved in your standard development.
We have members of NGA, we have practicing architects, engineers, and fabricators all involved in the committee. So FGIA and NGA, which incorporated Ghana. So FGIA is the IGMA group combined with ARMA. we start talking about glass fin standards, and they was talking about stability and strength for design loads, but they were not getting into these post-damage. And so the back end of this, which is talking about the engineering, the strength of glass, the different types of glass, and why mixing the stability equations from Australia and the glass strength from the US gives you unsafe results. Try to get consistency in that part of it. That's the other half of the big fat document that you're talking about. And since we've been progressing well on that, both NGA, Ghana, and FGIA, which is IGMA, ARMA, are saying, well, let's concentrate on this one, try and get it all right. It's quite possible that the strength and stability section will be the first piece to come out, but it won't address the things that I've just been talking about. It'll just say, here's a piece of glass, it's strong and it's stable. And it will probably include 2 or 3 line items, just say, select an appropriate level of post-damage behavior. Not the way that I would choose to do it, but it's quite possibly the way that it'll be released so that we don't cause too much shock to the industry. Which will leave it for people to specify for either the authorities to specify or for the project architects to specify as they see fit. And that'll give us a bit of a transition.
Richard, did you talk a little more about, I think it was the Shanghai Airport. Was that a retrofit of that film?
That would be Changi in Singapore, I think, what you're talking about. Yes, so the film was a retrofit. I was one of the consultants that was involved in the design and the engineering. We did all the calculations for that project. And it was recommended against using monolithic fully tempered. And the largest of those improbable loss of strength elements and imperfection in glass, spontaneous fracture from nickel sulfide inclusions is the most frequent. It's a teeny tiny little stone like a grain of sand, and when it's hot, it likes to be in a state that's smaller, and then as it gets to room temperature, it likes to grow. And it's a bit like putting a glass bottle full of water in the freezer. And when the water turns to ice, it likes to grow by about 4%, which is about the same as what this little stone does, except it happens again coming to room temperature, the opposite way around. And that causes it to grow, and combined with the tension that's in the middle of fully tempered glass, it initiates a crack. And once you initiate a crack in that tension zone, it just spreads through the entirety, as we're used to seeing in fully tempered glass. And
there's not really any way to check for those inclusions.
Correct, they're too small. So how they do kind of check for it is the rate at which it changes to the bigger piece depends on what temperature it is. And it turns out that if you take it to 280 degrees C, which I don't remember what that is in Fahrenheit, but it's 2.5 times boiling water. And it's below the annealing point of glass. Then these stones turn to the larger size faster. And after about 2 hours, you've got rid of 99% of them. And what it does is it causes the glass to blow up in the oven rather than on your building. And so the idea is if you do what's called heat soak testing on fully tempered glass, then you've got rid of 99% of these spontaneous fractures, and your glass should be much more reliable against spontaneous fracture. It's not perfect, but if you're talking about the difference between having a big building and having one piece break versus 100 pieces break, people just go, I can live with one piece breaking. Okay. Once you get to about the third, fourth, or fifth piece, people start getting really upset about it and really concerned about the risk that it represents. So 2 orders of magnitude change in the risk is still really worthwhile, and it's worth spending the money to do that with fully tempered glass. The idea with Changi Airport was said, well, the glass is still hot as it comes out the tempering oven. Why don't we just cool it and hold it at this temperature? And then if there are stones in it, it should break at that point in time or be good for thereafter after. They either held it at a temperature that was too high, didn't leave it long enough, or the process didn't work. But for whatever reason, they continued to get nickel sulfide, spontaneous fracture, and the safety film was the way that they addressed it without having to pull all the glass down. So, by design, laminated would be better. By necessity, safety film is a really great backup plan for something that's already in place.
All right. Well, thank you so much.
All right. You're welcome.
I did say I would open up. I'm going to click the allow to talk buttons on our attendees. If you guys would like to unmute yourselves and say hello, please do. But if not, you're all welcome to go on your
Richard
way.
and Janelle, you guys were both terrific. Excellent presentations. Thank you very much.
Thank you.
Thank you. Good to be here.
And thanks for your questions, Cliff.
Oh, you're welcome. I've done some research on that hurricane resistant glass, and I know that was why I asked the question about chemical tempering, because the results of the testing are that what they do is they chemically temper the inner light of a hurricane resistant glass, and that for some reason, which I don't know, limits the distance that the glass flies into the room. That's why I asked that question.
I'm not sure about the flying into the room, but what hurricane glazing, that there is a lot of different strategies on how that stuff could and should work. One strategy is you laminate it and you make the laminate strong enough that even though it gets hit and it breaks everything, it acts like a big piece of plastic that it is, and it just sort of flops in the cycles. One of the other strategies is that you've got 2 plies of glass, the outer one gets hit, it gets broken, and it slows down the impact, and then the second one just needs to be really strong to take 100% of the load, but you, fingers crossed, doesn't get hit a second time to break it. Now, the other interesting thing with chemically strengthened glass, and that gets used a lot in railway cars, because being really strong, it can be very thin and very light when you're trying to move it. Saves weight, saves energy. But the other thing is, when it's really thin, it's springy. So when it gets hit by a rock or a piece of wood, it just bounces back out because it springs in, absorbs energy without fracture, and then bounces back out again. And so chemically strengthened can have good impact resistance because it's a bit of a trampoline, rather than I'm stiff, it gets hit, and then initiate that star point. Once you start the crack, it penetrates through. So it can be quite different in its behavior in an impact situation because of it being thin and strong.
I'm very pleased that you kind of reinforced some of the things that I've heard from Chris O'Hare about tempered glass. You know, you really should not use it over 25 feet. If it's above 25 feet and it falls, you know, it can have those serious,
Right.
effects. So
Yeah, so the one of the other things which is hotly debated is where do you draw the limit? Okay, so we start thinking about once we get anything under 10 feet, IBC is sort of like you don't even need a catch screen on it, even if it's less than 15, if it's more than 15 degrees from vertical. And under 10 feet, generally regarded as okay. Polling the glass producers, when we start getting into glass fins, once it starts getting above about 12 feet, we start seeing a significant uptake in laminated glass. Once we get to 18 feet, that's about as far as you get on a single jumbo, but it's also where the old Ghana glass fin tables went to for monolithic glass. And so that's kind of where we've drawn the line as, under 18 feet, monolithic's probably okay. Above 18 feet, you should start thinking about laminating it. There are a number of people that have advocated for 24, 25 feet. So you're in that sort of gray zone between 12 and 24 feet. I think everyone agrees below 12 feet, it's fine. Everything above 25 feet, there's general agreement that you want to have some retention and redundancy in place. In between, probably depends on the project you're working on.
that's pretty much in line with what I've heard.
Good to hear.
Where does kind of energy come into the calculation for windows like these?
Yeah, so glass design has many aspects, and the thermal energy performance is pretty much independent of all of this. That's something which, the type of coatings which we have in play, thermal fracture absorption, that's certainly something which we want to take into consideration. But, we like to keep structural strength on one hand, we like to keep serviceability and displacement on another piece, and thermal performance on another piece, and procurement and fabrication as another piece of the puzzle. But all of them have a place, and thermal is probably getting more excitement just because it's en masse affecting the building than structural applications. But we can certainly build some beautiful things if we start thinking about how to use glass to its full potential. Of course, we could start digressing into multifunctional glass and electrochromics, both visual and infrared, and self-tinting, and all sorts of exciting things. So
I see OITC as a whole nother topic to discuss. OITC, with residential towers, big tall buildings that have all the sounds from the street coming up into their apartment.
Yeah, again, another aspect. This is really talking about the structural performance. Acoustic performance, again, lamination can help. Multiple layers can help. Different thicknesses also kick into it, but it's this is not intended to be the whole piece. It's just a little piece of what it takes in designing glass. We get into picking colors, picking shades, picking thermal performance, optimizing for glare versus visible light transmission. It's not always optimal to go, not a one size fits all, and that's why we need to be considering our glass very carefully when we're thinking about different projects that we're working on.
Awesome. I think we can wrap it up there. I look forward to seeing folks at the next meetings. I think we're definitely going to stay virtual for the time being, but hopefully we'll get together again soon. And everybody take care and stay safe. Do you want to say something, Matt?
Yes, I just wanted to mention that Puget Sound Chapter CSI is still intending to be live for their annual trade show. It's the end of March at the Bell Harbor Center. It's called Prospect 2022, and you can register through some of the vendors and others who are going to be there.
When is that?
It's March 22nd, I believe.
Yes, I've been dying to go to a prospect.
March 20th.
I've lived 7 years in the Pacific Northwest, and I have yet to go to a prospect.
Well, it's a good show, Cliff. You
The
shouldn't miss it.
details are on our website. All right. Thank you, Nathan, for hosting today.
Yeah, and thanks again to Janelle and Richard. We really appreciate your presentations. I liked how Beth kind of stitched them together with the favorites of the Northwest. But we appreciate you guys putting the time in and your thoughtfulness. So everybody have a great evening. We'll see you again soon.
Thank you.
Thank you.
Bye-bye.
Take care. Good night.